Hello everyone, welcome to Math 153, Statistical Reasoning. I wanted to show you one of my favorite problems. This is a problem that you would behoove yourself to study and practice because it's a good question. I would think if I were writing the test, and I didn't, it's written by a committee, but if I were writing the test, I would probably put this question on it because it's such a favorite question of mine. So let me share the question with you. In the book, it's on page 159, and it's number 31 in the exercises. Let's see where it is. In the exercises, it's in 4.2, and it is number 8. And this is a really, really good question because it makes you think a little bit. So what's going on here? And it almost looks as though you'd need some knowledge of electricity and circuits, and you actually don't. The idea goes back to something we talked about. One reason the multiplication rule, one application of the multiplication rule, this is back on page 154 of your text if you remember it, is the idea of redundancy. And if you have more than one part that could fail, then you're safer, right? You want 4 engines on an airplane. You don't want just one, because if there are 4 and 1 goes out, well, 3 are still working. You could land safely. And if you have 1 and 1 goes out, well, then maybe not, depending on where you are. So let's look at this problem. This problem has 2 different configurations, and I think you can see my cursor. So there are 2 surge protectors, and that's the P and that's the Q, and this weird thing that kind of looks like a plug is actually a plug, and this thing that's labeled TV looks nothing like a TV. Well, it kind of looks like a TV. My TV's about that shape. It's bigger though. Anyway, this is the TV set. And the idea is we have this delicate TV set and we don't want to blow it up in case there's a lightning storm or something. And so what we do is we plug it into a surge protector. But you know, surge protectors aren't perfect. Sometimes they let electricity through. High voltages, dangerous voltages. And so me being the worrywart that I am, I've plugged in 2 different circuit protectors. And then I think, well, wait a second, which way should I plug it in? Should I plug it in like this, which is the electricity comes from here into the first surge protector, and then assuming it gets through, it goes into the second surge protector, and assuming it gets through, it goes into the TV and powers it. That's the series because these are lined up in a row in a series. Or should I plug it in parallel, because parallel has a lot of useful things in electronics. So here the electricity comes and it has a choice of coming through either P or Q before it gets to the TV. And what they tell us is that each surge protector has a 0.92 probability of working correctly. So 8% of the time, I shouldn't tell you this yet, 92% of the time it will work great. And that begs the question, it suggests the question of, well, how often is it going to fail then, right? If it works 92% of the time, and here we're using our complement rule, that means that 1 minus 92%, 100% minus 92%, or 1 minus 0.92, it means 0.08 probability that it will fail, it will work incorrectly. And what we're interested in is we don't want to damage the television. This not is very important. So if the 2 surge protectors are arranged in series, what is the probability that a voltage surge will not damage the television? So having looked at that, and all we have to remember is the 0.92, let me share a whiteboard with you. And I'll draw this little thing. It looks like this. And it comes through P, and then it comes through Q, and then it goes into the TV set. And we're hoping it doesn't damage. So the probability of it works for 1 is 0.92. The probability that it fails is 1 minus the probability that it works, right? This is my complement rule. And you can use a calculator for that if you need it. We'll use a calculator in a minute because we'll start multiplying multi-digit numbers. But there you go. So the probability TV damaged. Well, how would the TV get damaged? Well, for the TV to get damaged, P has to fail. Because if P works, well, then the TV doesn't get damaged. The bad electricity is stopped at P. And then after P has failed, Q has to fail. Because if Q works, well, then the bad electricity is stopped by Q, and it doesn't damage the TV. So the probability that the TV is damaged is the probability that both fail. And then we have our multiplication rule, the probability that P fails times the probability. We have to ask ourselves, right? It's a thinking class, not a math class. You're waiting for me to say it, I know. We have to ask ourselves, can we actually use the multiplication rule? And remember, we can use the multiplication rule safely if these two failures are independent events. And so, I don't know, actually. I'm thinking if P and Q were sitting right next to each other on the store shelf, and if P and Q, why are they sitting next to the store and next to each other on the store shelf? Because they came out of the same box. And why were they in the same box? Because they were manufactured at the same plant, right next to each other. Well, yeah, then if something's going wrong, it's possible it's, Fred was on the production line that day, and, Fred, he's fouled something up. So, this is a little risky, but they haven't given us any other way to do it, right? We don't have any other information. So let's suppose, okay, these are different surge protectors, right? You bought one in August and you bought one in November. And so Fred wasn't working both times. We're going to assume that these are independent events. And so we can use our multiplication rule. Well, then it's just a matter of plugging in, and we know what it is. We know that the probability that one fails is 0.08. And so I write that 0.08 times 0.08. And I'm thinking this is, the hard part for me is the number of decimal places. 1, 2, 3, 4, because I know 8 times 8, that's 64. But I need 4 decimal places. And it's easier if you have a calculator, but I don't want to take the time. What's this? This is the probability the TV is damaged. What did the problem ask? It says, part A, if the two surge protectors are arranged in series, that's what we have, what is the probability that a voltage surge will not damage the television? So the probability that the TV is not damaged equals 1 minus the probability that the TV is damaged. And this is an interesting problem. People love this problem. It would be a good test question, wouldn't it? The reason it's so interesting is you get to use this complement rule twice, right? Once for each individual and then once for the combination. And so we say 1 minus 0.0064, and that I can do in my head. It's 9936. So what's the likelihood that in a situation where there's a voltage surge, what's the likelihood that the TV would be damaged? The TV would be not damaged. It's almost guaranteed. I mean, we're not 100%, but we're 99.36%. We're really, really good. I think that the TV is going to be okay. I'm feeling good about this. Let's turn on the TV and watch a show. Okay, so there's the first situation, part A. Let me key it in. You can't see me keying it in, but I'm going to key in 0.9936. 0.9936. It says do not round, and then it says fantastic. Oh, I'm feeling good. And what we had to do was we had to take the 0.92 and we had to subtract, and then we had to multiply those to get the probability that both fail, and then we had to subtract again to get the 0.9936. So it's kind of a few steps, but if you talk yourself through it, the way I've written it out. Okay, let's do this one, the parallel configuration. If the two surge protectors are arranged in parallel, what's the probability that a voltage surge will not damage? I don't have a lot of knowledge of circuitry, and you don't really need a lot in this question. I mean, there's lots of things you can do in an electronics class about series and parallel, and it affects resistance and capacitance, and oh man, there's all this. Well, they're math rules, so they're not hard. They're just math. The hard part would be the thinking. Oh yeah, there we go again. Anyway, what do we want to know? We want to know the probability that a voltage surge will not damage. And I have no idea what the probability is, but there's a not in it, and so I'm suspicious that this equals 1 minus the probability that it damages. And I'm thinking that's 1 minus the probability that either one fails. If one of those surge protectors fails, if P fails, well, in comes the bad electricity and it goes right through P and blows up the TV. And if Q fails, in comes and right through and it blows up the TV. So if either one fails, then we're going to have issues, right? Well, what does either one fail means? That means it's the opposite of both work. If both work, then we're okay, right? Does this make sense? This is kind of the tricky part right there, is going from the probability either one fails means the opposite probability of both work. And if you're maybe you're a cleverer person than I am, maybe you can go from not damage to this step I'm about to get. But since I saw the not, I was led down this path, and this either one and both, I kind of know that. If you want to go from here to there, it is possible to do that. And what do you end up with? Well, look, the 1 minus the 1, well, those cancel out. And the negative minus minus makes a plus, the reason why we won't discuss. The probability that we don't damage the TV is the probability that both work. So if you are that sort of mind, and you look at this and you say, well, the only way you can not damage is if both work, well, then you can go from here to here and you don't need all those intermediate steps. And it makes the problem simpler. But sometimes people don't see that, and so I wrote it out. Or maybe I didn't see it, and so I wrote it out. Well, what's the probability that both work? Well, that means P works and it means Q works. So let's write that. Equals a probability P works and Q works. That's what it means to say both work. Hey, there's an and. We have a multiplication rule for this. The probability that P works times the probability that Q works. And here again, we are assuming that the probabilities of failure on either one are independent. Otherwise, we couldn't use our multiplication rule. And we happen to know what the probability of P working is because they told us in the problem it was 0.92. And multiplying those together, you get 0.8464. That one I know. I did that in my head. Whoa, that's impressive. I didn't do squat in my head. I just memorized it a few years ago. So what's the probability that this configuration, the parallel configuration, won't damage the TV? It's about 85%. I'm feeling pretty good about that, but not near as good as I feel with a 99.36. So I'm keying it in. You can't see it. It says fantastic. This is a nice example of this combination. It's a fabulous question. This is why it would make a really good test question if someone were to be tested over this stuff. Hint, hint. Okay, so it says continue. Well, let's continue. And it says arrangement should be used. Well, scroll back up. I'm 99% sure that it won't be damaged, or I'm 84%. I'm thinking series has a much higher probability, so I should use series. So parallel, higher, nope. Series is better because it's lower, nope. Series is better because it's higher. Yeah, that's the one I like. So anyway, fabulous question. And you realize that if you practiced this a few times, how much work is there, you know? I'll show you how much work there is. This is 91. Oh, wow, 91. So what am I doing? 1 minus 91, that's 0.09. 0.09, square it. It's 0.0081. Subtract from 1, 0.9919, there. But if they both work, well, 91 times 91 is 8281. So that's how hard it is in theory. I mean, you have to be me, but even with a calculator, it would only take me a minute. But you could practice this and be very good at following those steps. Point made. Okay, it is a really good question. It's a great question.